I'm really delighted to introduce to you all Dr. Pete Lawler, who's the Director of Hemostasis Research in the Aflac Cancer and Blood Disorder Center. He's also Professor of Pediatrics and the Hemophilia of Georgia, Inc. Chair of Hemostasis. He received his bachelor's degree from LSU in chemistry, which he loves chemistry, and an MD from St. Louis University, and did a 5-year combination of residency in internal medicine and fellowship in hematology oncology at the University of Iowa. During his time as a resident, the Division of Hematology Oncology instituted a program whereby residents did 2 years of laboratory research. That experience reinforced Pete's conviction to become a physician scientist. He received additional fellowship training in hematology at the Mayo Clinic and accepted a faculty position in the Department of Internal Medicine at the University of Vermont in 1984. In 1990, he came to Emory, initially in the Department of Internal Medicine and then in the Department of Pediatrics. And you may recognize him because he's actually sitting in the back yesterday when Dr. Jane was giving his talk and was asking Pete if he remembered the trailers, which apparently he does. That's where did you do your research in trailers?
Saw patients in trailers.
Saw patients in trailers, imagine that. So that's a little bit about his past. He's also directed an NIH-funded research program for 30 years towards understanding the basic mechanisms of hemostasis and improving treatment for patients with hemophilia. His research team led the drug discovery process and clinical development of Obizur. Is that right? Obizur? It's a recombinant coagulation factor VIII molecule that is used in the treatment of patients with hemophilia. Very impressive. Dr. Lawler is an incredibly rigorous scientist who is very thoughtful and serious about the scientific method. So when I was talking to him when he was telling me about the idea of this talk, I found his scholarly ways to be really insightful and truly appreciated him putting this talk together to teach us about the importance of enhancing reproducibility in research. Especially when it comes to the fundamental basic science research, the answer really isn't always as easy as you would think. And so I'm looking forward to Dr. Lawler sharing his insights and thoughts on experimental design, the art of scientific measurement, and how that translates to the NIH policy on enhancing reproducibility in research.
Thank you. Can you hear me back there? Good. Okay. Thanks, Stacy, for that introduction. Today, I'm going to talk about what has been called the reproducibility crisis in research. In recent years, there's been increasing attention paid to the fact that many, if not most, claims made in science turn out to be false. This problem is widespread. It includes both the social sciences, physical sciences, as well as the biomedical sciences. And it spawned a vast literature. Last year, there were 899 publications with the word reproducibility in the title. This problem also has received attention in the lay press, and because a lot of research is done with publicly, with tax dollar funding, we have had a lot of scrutiny from the NIH in terms of trying to improve the reproducibility in research. So the NIH has come up with a formula for enhancing reproducibility. And they say that to do that, we have to do it through what they call rigor and transparency. They have a guidance on rigor and reproducibility in grant applications, and both applicants and reviewers are supposed to follow this guidance. They also have tutorials on their website for how to enhance reproducibility in science. So what is reproducibility? It's controversial, and it's spawned a literature just on what people are talking about. Goodman and co-authors published an essay in 2016, which actually said that reproducibility comes in 3 flavors. The advisory committee to the director of the NIH published a paper this year called Enhancing Rigor, Transparency, and Translatability in Animal Research, in which they adopted Goodman's guidelines. And I think this is a good working model for what we are talking about with regard to reproducibility, because it really gets to the heart of the nature of the scientific investigation and making truth claims versus claims that are false. So one form of reproducibility is methods reproducibility. That's when you can do the procedures and reproduce them exactly. But this definition is kind of problematic because anybody that's ever done a procedure in the laboratory or conducted a clinical trial knows that you can never reproduce everything exactly. The second type of reproducibility is results reproducibility, which is when, if you repeat a procedure as closely as possible, you get the same results. But again, that's problematic because, as we'll see, you never achieve the same results in any scientific investigation. But what can be reproduced is what's called inferential reproducibility, which is kind of a fancy name for something that I think can be described as follows. What Goodman says is what scientists are really concerned about when they debate research reproducibility is the truth of research claims. Truth claims are qualitative statements that we make based on methods and results. Frequently, those methods and results are quantitative, they're numbers, but we make qualitative statements. An example of a truth claim: messenger RNA encoding SARS-CoV-2 vaccines prevent COVID-19. The degree of belief that we have in a truth claim is based on how much evidence supports it. For example, all of these claims at one point or another were controversial, but now no one doubts that the chemical formula for water is H2O. There's increasing evidence that the Earth is warming due to human activity, but there are some good scientists that don't accept that at this time. Francis Collins and Lawrence Tabek at the NIH, Collins is the director of the NIH, published an essay in 2014 in which they cited some causes of poor research reproducibility. One is poor experimental design that I'll talk about in a minute. Another is poor training of researchers in experimental design, including statistics. And I think that's one of the great things about the Department of Pediatrics here. As you are incoming fellows, you're head-on meeting this problem of trying to get physicians, scientists trained to do good work. This poor training of researchers includes poor statistical training that I'll talk about in a few minutes. Poor transparency, not being able to communicate what the results are. Unpublished negative results. It's a bias in science that negative results don't get published. And if only positive results get published, but there are a lot of studies studying the same thing that are negative, then that can lead to the false claim that the result that was reported positive is the true results. And then in their essay, they point to some more unsavory causes for poor reproducible results. Overemphasis on making provocative statements rather than presenting technical details. Everybody wants to tell a compelling story, and a lot of times the storyline strays away from the experimental evidence. Overvaluation by academic centers, funding agencies, and publishers of high-profile research. There's a emphasis on having the most grant money, being number one, making a great discovery. And sometimes these claims are made in order to create more importance around one's work when there is not sufficient evidence to support the claim. And finally, financial interests. Some investigators have ties with industry, but it's important to recognize that as professional scientists, we all have a financial stake in the outcome. Our promotions our grants and our salaries are based on success in the research laboratory. Some elements of poor experimental design that Collins and others have pointed out, small sample sizes. This isn't really a statistics lecture, but I'm going to touch on some points that I think should become clear to you as you go through the rest of this week. Small effect size, that's when you make an observation that's statistically significant, but the effect isn't really that large and it's not really biologically or clinically significant. I'll show an example of that in a minute. Some studies, but not all, require blinding from the investigators that are doing it. Some studies, but not all studies, require a randomization of the subjects. Failure to account for effects of sex differences has become increasingly recognized as a problem for poor reproducibility. Testing too many variables. If you test enough variables, you're going to find a significant difference. But then if you were to repeat that test with the same number of variables, those differences frequently disappear in a statistical sense. And then over-reliance on unproven analytical procedures. I think we place more confidence on procedures which are more tried than true than newer procedures. So what is scientific rigor? The NIH application is the strict application of the scientific method to ensure robust and unbiased experimental design, methodology, analysis, interpretation, and reporting of results. That doesn't seem very helpful. I think what they're saying is do good science, but what is good science? How do you do that? Philosophers on the outside looking in have a hard time explaining what science is and how it creates knowledge. We do know that science somehow leads to spectacular results. Rocket ships going to Mars, mRNA vaccines. But science is messy and full of controversy. As Einstein said, if we knew what we were doing, it would not be called research, would it? So I think it's important to recognize that although we try to reduce the mistakes that we make in science, there is always there are always going to be mistakes. And amid all the din and clamor associated with scientific findings that are reported from year to year, in the long run, as Collins has pointed out, the scientific process creates truths that can be built upon and provide an ongoing momentum for scientific endeavors. Okay, sorry. So if you're going to get involved in research, sooner or later, you're going to come face to face with statistical problems. Florence Nightingale was a pioneer in early epidemiological research. She was a quantitative thinker who developed methods for graphical representations of data that we still use today. She said, to understand God's thoughts, we must study statistics, for these are the measure of his purpose. Ernest Rutherford, a physicist, he was no scientific slouch either. He discovered alpha and beta radiation in the atomic nucleus. He said, if your experiment needs statistics, you ought to have done a better experiment. So let's examine the case for Rutherford and the Nobel laureates in chemistry and in physiology and medicine last year. Jennifer Doudna and Emmanuel Charpentier won the Nobel Prize for their discovery of the CRISPR-Cas system, which is what is used now for gene editing. When you look at their seminal paper, no statistical analysis. Charles Rice won the Nobel Prize for discovery of the hepatitis C virus. When you look at his seminal paper, no statistical analysis. Another case for Rutherford is statistics and transparency. This is a paper from a research group that appeared this year in Lancet, on which they're describing antibodies in human subjects that were immunized with SARS-CoV-2 vaccines. And I've cut and pasted some of the language in their methods. It says there's a type equal basic argument to avoid any assumptions about the normality of data. There's a statement, the LMR function of the regression modeling strategies, RMS package in R using formula IC50, etc. Yikes. Frequently, it's hard to understand scientific papers in which there is a lot of statistics, and that's a problem of transparency. This isn't really confined to clinical research, and this is an example of statistical methods that were published in a paper in which some investigators were looking at pathways involved in the development of leukemia. And here's a whole bevy of statistical tests that they use. Many of these are familiar to basic researchers, but some of them are not, including to me. I have really no idea what a Benjamini-Hochberg false discovery rate is. So let's look at the case for Nightingale. Scientific endeavors are characterized by unavoidable uncertainty. And statistical methods, by definition, are those procedures which are used for making decisions in the face of uncertainty. There's really, I think, three sources of uncertainty in science: random error, systematic error, and population differences. And I'm going to discuss all three of them in turn. Random error was identified a long time ago. The analysis of random error goes back to 1572, when a new star appeared in the sky. Can you imagine you're looking at your favorite constellation and all of a sudden there's just a new star just popped up. That's what happened. That star is now called a supernova. And the prevailing dogma was that anything that happened that was new in the sky, it happened between the Earth and the Moon. But there was another competing hypothesis that this star was much further away among the so-called fixed stars. So 12 different research groups tackled this problem, and it could be tackled because astronomical science was advanced far enough at the time that you could make quantitative predictions of one hypothesis versus the other based on the measurements. So they made the measurements, and the 12 different groups got 12 different answers. So Galileo, several years later, did a literature search on these observations and published an analysis of the problem in 1632. And the result was a profound generalization from experiment. He said there is one number that gives the distance of the star, the true distance. In science, there are truths, and those truths are what we're trying to seek. But no observations are free from errors. While all these scientists were saying that they had the true measurement and the other guys were wrong, he recognized that nobody had made an absolutely accurate measurement. He also observed that observations or errors tend to be distributed symmetrically about the true value. I'll talk about that in a minute. And small errors are more frequent than big errors. So as an example, I'll take an example from an undergraduate chemistry text in which they're measuring the volume dispensed by a 10 milliliter pipette. they dispense the volume, and then they measure the actual volume by weighing the sample and using the density. And what they find here is shown on the right part of the graph. The results have been placed in the ranges called bins. And this is an example of what's called a histogram, which is a really important type of data presentation in statistical sciences. And on the x-axis is how the errors or the measurements have been binned. And on the y-axis is the relatively frequency of the observations. And although all these measurements are within 0.3% of the nominal value of 10 milliliters, they're all associated with error. They're also kind of symmetrically distributed. If you can see that there's a symmetry to this histogram, and you can definitely see that small errors are more frequent than large errors. So to go further, we have to review a little math. Mathematical functions allow for a correspondence between x that produces y. So in one of our simplest functions is a function equation for a straight line. Y equals f of x equals mx plus b. M is the slope, b is the y-intercept. In statistics, m and b are called the parameters. So with that brief math review, in 1809, Carl Gauss, who was studying errors involved in astronomical observations, published a derivation in which he produced what's called the normal density function, also called the normal distribution. And the assumptions that he made were Galileo's assumptions, which are observations are distributed symmetrically about the true value, and small errors are more common than large errors. And the result that he obtained is shown here. This is the function. Here's f of x, here's x. And if you plot this function, you get this curve, which I think many of you will recognize as the famous bell curve. And the other components of this function are mu and sigma. Those are the parameters of the function. Mu is the mean, sigma is the standard deviation. The probability of x being between two values, in this case 0.5 and 1, is equal to the area under this curve. And this really provides the basis of most statistics that you're going to run into. Because we're talking about the frequency of observations here, people that use this type of analysis, which is going to include most of you if you ever do any research, they're called frequentists because they're interested in the frequency of events. And our journals now are littered with graphs like this, where comparisons are made in which we're trying to compare two means and asking the question, are these means significantly different? And if there's an asterisk there, then it is statistically significant. But this is also an example of statistical significance, which isn't very impressive. I mean, here we've got levels going from 40, maybe 40 to 45, and they're claiming statistical significance. And what we see frequently in journals is people making inferential statements about true statements that are based on these quantitative differences, which are small, but they're making qualitative differences because of them. This is what Francis Collins was talking about when he's talking about small effects. Now, if we go back to this volume experiment and we calculate the mean and the standard deviation, we're calculating technically what's called the sample mean and the sample standard deviation. 50 measurements are made, and this is the normal curve that fits the data. And you can see that, yeah, it looks like it's fitting it, kind of, but one of the criticisms that are raised against frequentists is that we frequently don't have enough data to establish whether the data is distributed normally. And there are statistical tests to treat that, which I won't go into. However, it is true that sometimes data are normally distributed. This is an example of a paper in which they're looking at the quality of fit to a particular biophysical method, which isn't important. But what is important is that this particular model, generates a series of data curves, and they fit the data and the curves. You can see that there are curves that are fitted to the data. And if you were to look real close, you would see that the curves don't exactly go through all the data points. This is a data-rich experiment. There's 76,000 data points. And on the right side is the frequency as a function of the errors. And I think you can appreciate that in this particular case, the data are normally distributed. But frequently, we run into situations in which data is not necessarily normally distributed. So in 1846, Adolf Quetelet reported that the variation of male chest circumference could be described by a normal distribution. He had access to data from the Scottish Army in which they measured the chest circumference in 5,732 Scottish soldiers. Why the Scottish government made these measurements, I have no idea. But Quetelet was an astronomer. He was familiar with experimental error, and he was familiar with the normal curve. And this is his fit to the data. And I can hear you all giggling up there, but this is the basis for clinical trials that we do today, because biological traits, a lot of them tend to be normally distributed. Serum glucose, height, all kinds of things tend to have a normal distribution or approximate normal distribution. So that now we're going from a situation where you're making laboratory measurements and measuring those errors to a situation where there's a normal distribution, but it's not a laboratory error, it's a fundamental process in biology. So why do measurements and biological variables tend to be normally distributed? A measurement typically is an aggregate of a large number of elementary errors. If you're using an electronics instrument, there's a lot of electronics jitter. If you have to manually read something on a dial, your ability to do that varies. If you're making an astronomical observation, there's fluctuations in the atmosphere. And all these errors kind of go back and forth. They're random. And when they accumulate, they tend to produce a normal distribution, which Gauss showed. In the case of biological traits, a lot of biological traits are polygenic. There are many genes contributing, and each gene is perhaps randomly being expressed in somewhat random fashion, in the sense that the amount of insulin that you're putting out at any time is a function of your pancreatic islets, and they're just not pumping out a constant amount. So these tend to accumulate, and biological variables, even though they're not errors, they are normally distributed. Another reason why things in nature tend to be distributed normally is due to the central limit theorem of statistics, which says that the sample mean of a random variable, like let's say glucose, approaches a normal distribution as the sample size approaches affinity. And that's true even if the random variable itself is not normally distributed. The mean is normally distributed. So scientific truth claims are often based on the analysis of random errors. When you're doing a statistical test, you're testing based on random errors. The quantitative application of this type of error analysis falls into three broad categories. One is making point estimates and assigning confidence limits, like establishing normal ranges, establishing means in different populations, testing two drugs to see if one's better than the other, drug versus placebo. And the third is assessing quantitative models, for example, trying to fit drug clearance data to pharmacokinetic models. The most commonly used distributions in statistical inference are student's t distribution, the F distribution, and the chi-square distribution. These distributions all assume that sampling is from a normally distributed population, which is why I'm spending a lot of time on the normal distribution. When this isn't the case, there's a whole field of statistics called non-parametric statistics, because we don't really have the parameters that I talked about in the normal distribution to rely upon. So that's random error. Now, systematic error is different. And to give an example of that, this comes from, this example is used over and over again, and perhaps many of you have seen it. This would be an example, for example, if you had 4 military recruits that were in rifle training and basic training in the Army. And this recruit, the shots are centered around the bullseye. We would say the measure of how scattered the points are is a measure of the precision, and how close those points are is a measure of the accuracy. This shooter has, the precision is the same, but he's missing the target in a systematic way. And that's perhaps because there's a problem with the way his gun sight works. He's pointing at the target, but the sight's messed up. This shooter is accurate. He's pointing at the center of the target, but there's a lot of scatter. And this shooter has 2 problems. He's not accurate and he's not precise. So one of the problems we have in the real world is we don't know what the target is. We never know the truth in science. We can only make the measurements and then make some inference about how close to the truth we are. So the best way to get around this is to assign what are called reference standards, if possible. If you do have a reference standard, then when you make a measurement, you can see how close you are to the reference standard. But the reference standard is not really the truth, it's just a standard. So 2 examples of reference standards. My favorite standard is Legrand K. It's a chunk of metal in Paris. It formed the reference for the standard of mass from 1889 to 2019. And it was defined as weighing exactly 1 kilogram. And every measurement of mass, whether it was on an analytical balance in the laboratory or on your bathroom scales, ultimately were traced back to this standard. Another standard, for example, is the calcium carbonate pH standard, which is issued by the U.S. National Institute of Standards and Technology. All the pH meters, all commercial pH meters, ultimately are standardized relative to this standard. Systematic errors are hard to detect and evaluate. And in contrast to random errors, there are no mathematical models for systematic errors. For random errors, we have the normal distribution. There are a lot of other distributions, and that's frequently all judgments are quantitative judgment based on that. But we don't have any way to measure or quantitate systematic errors. And in practice, in the real world, many, if not most measurements are dominated by systematic errors and not random errors. So identifying and reducing systematic error requires experience and judgment. There's no formula for doing so. There are two broad ways to go about doing it. One is creative. You just try to think of things that you could be doing wrong or things that could be possibly giving you a systematic error and try to eliminate them. The second is to compare the results of two independent measuring processes that are using two different principles to measure the same thing. For example, you can measure messenger RNA levels using qT-PCR, or you can measure messenger RNA levels using northern blotting. If you get an answer that's pretty close, they're never going to be the same. You have less concern that there's systematic error. If there is a big difference, then there's a problem with one or both of the methods that are using. There are many causes of systematic error in the laboratory. You may have multiplied when you should have divided, arithmetic error. You may be using an inappropriate and incorrectly calibrated pH meter. You may be measuring weight loss in animals and you haven't been zeroing the balance. One of my favorite examples, which I saw happen here at Emory, as some of our intrepid researchers were using tap water, didn't know it in their cell culture experiments. So anything that was in the tap water that's not in pure water was contributing to their results. Confidence limits is a really important concept in measurement. Suppose you have 4 mice, you subject them to an experimental diet, and you measure their weight gain after 3 months. What can we say about the average weight gain in that population? If the population is normally distributed, you can use students' t-distribution, and you get an estimate of the population mean and the confidence limits. In this case, the answer is 1.27 plus or minus 0.03. We see confidence limits reported in both basic science and clinical literature. It's more commonly reported in clinical studies, which is more appropriate because confidence limits give you more information than just reporting the standard deviation, which is what we tend to use in laboratory measurements. It's important to recognize that confidence limits pertain to the precision of an assay or a measurement, but they don't say anything about the accuracy of the assay. And confidence limits, it's a tricky concept. When the idea of a confidence limit was introduced in the 1930s, a lot of statisticians had a real problem understanding what it meant. And there are a lot of controversy, and there may still today be some controversy as to what does it mean when we report a 95% confidence limit. This is the currently accepted correct way to state the results of this experiment, which is a real mouthful. Based on this single experiment, the claim is made that 1.27 plus or minus 0.03 grams contains the population mean. If for each such experiment the same claim were made for the interval corresponding to that experiment, then 95% of such claims would be true in the long run. And you could ask me, well, why don't you simplify that? You really can't take out any words in this statement without messing it up. And it's really hard to paraphrase what it means. But I think one of the key things is that what the statisticians have foisted upon us are these terms, claims. We make claims, and then we have confidence, but we only have like 95% confidence or 68% confidence. And that's the nature of the beast in statistical inference, especially in frequentist statistical inference, where we're always talking about probabilities in terms of the frequency of events. It's incorrect to say that the probability is 95% that the average weight gain is between is 1.27 plus or minus 0.03, and that is a common mistake that almost everybody makes. And I even make it you have to be really careful when you see confidence limits because you just want to have a knee-jerk response. Yeah, there's a 95% chance that the mean is 1.27 plus or minus 0.03. That's incorrect. So we talked about random errors, systematic errors, and now we're going to talk about populations, which is, I said systematic errors are maybe more important than random errors. Concept of population is, I think, more important than the concepts of random error and systematic error. In statistics, the totality of all possible outcomes is called the population of outcomes. We can never know the parameters of a population, mean, standard deviation, other parameters. We can only get estimates of them from experiment. Misunderstanding or over-interpreting the generalizability of the population being sampled is arguably more common than experimental error in the development of false scientific claims. So on the left here is an example of an essay which has really become a prominent item of discussion, which is how reproducible are mouse studies. The laboratory mouse is the most widely used animal, and what is being found is it's very difficult in some model systems to reproduce results from mice. And the reason is not because of errors made in the measurements, it's because you're looking at different populations. For example, in immunology, one of the most important things that has emerged in recent years is the role of the gut microbiome, all the bugs in the gut, contributing to immunological responses. And the gut microbiome can vary in genetically identical mice depending on where they live, whether they're at Emory or at CHOP, or even whether they're in the Whitehead Institute or in Emory Children's Center. So it's a real problem, and it's due to population differences, which can be really hard to identify. In clinical trials, for example, in a phase 3 clinical trial, patients can participate only if they meet rigorous entry criteria. You do a clinical study, you find some result which is significant, but this population frequently differs from the intended population that the drug would be used for. And then there's what's called the heterogeneity curse, which is that within clinical populations, there can be different subpopulations so that we're not dealing with Quetelet's Scottish soldier where we have a nice, two nice normal distributions that we can compare. For example, patient gets drug, patient gets placebo. They both are members of normal populations. Do the means differ? These populations are frequently more heterogeneous, and the statistical method is based on the assumption of a normal distribution or some other distribution don't necessarily apply. I'm also going to say a little bit about Bayesian statistics, which I don't know a whole lot about because it's complicated. But I would start with this. Does a subject with this EKG finding have coronary artery disease? So we have significant ST elevation. I know you're pediatricians, but I think you know that ST elevation is not good. How many people think this person has coronary artery disease? Nobody. How many? Okay, I got one. How many people would say no? 0. How many people? Oh, there's one. How many people would say maybe? Okay, good. So I think you've seen this before. The probability this patient has coronary artery disease depends on the prevalence of coronary artery disease in the population under consideration. If this is my EKG, the probability it's coronary artery disease is higher than if it's Dr. Heilman's EKG, because older males have a higher prevalence of coronary artery disease than younger females. So this prevalence in the language of Bayesian statistics is called the prior probability. And if you know the prior probability and the sensitivity and specificity of the test, you can come up with the probability that the patient has heart disease based on the positive test. That's called the posterior probability. And nobody disagrees with that. It's a very powerful way to make decisions in clinical medicine when you have that data. There's a fundamental disagreement between the frequentists and the Bayesians regarding the definition of probability. For frequentists, probability only has meaning in the case of the limiting case of a lot of repeatable experiments. Ultimately, in the case of an infinite number of experiments, you can say this is the probability. For Bayesian, the Bayesians have a problem with that because of the fact that in the real world, we're frequently confronted with small sample size, and also because we don't necessarily are dealing with normal distribution, there are ways that statisticians get around with that, but Bayesians think it's a problem. For Bayesians, probabilities are fundamentally related to their own knowledge about an event. And they often start with just a guess about the prior probability, and that really annoys the frequentists because it's too subjective. I'm going to say a few words about developing statistical literacy. Many of you may proceed, if you're going to be doing clinical research, to obtain a Master of Science in Clinical Research, MSCR. And when you do that, there is several courses that you can take that are listed here that will allow you to get formal training in statistics for clinical research. And this is the statistical training that's available for laboratory-based investigators at Emory. There isn't any. You kind of have to learn it on your own, some way, somehow. One way is to use statistical methods as a tool you have no hope of understanding. Automobiles now are unfathomably complex, but we all drive around. We use the automobile as a tool to get where we're going, but we really don't understand how it works. So I don't really have a problem with using statistics as a tool you don't understand. This is a photograph that I took of the window blinds on the 4th floor of Emory Children's Center where I work. Some enterprising graduate student has taped up an algorithm for statistical testing. How many groups are there? Is there more than 2? You better do analysis of variance. Is it normally distributed? Do a t-test. If you are going to do analysis of variance, how many groups are there? Do you need to do 1 or 2-way analysis of variance? Is the data normally distributed? If not, do non-parametric tests. It's a useful algorithm to pursue. The Journal of Biological Chemistry Instructions of Authors says, use PRISM as your guide to doing statistical analysis. PRISM is the most widely used software program for laboratory researchers. And you got to be kidding me. The problem, PRISM is a good program, but it has no documentation. You just like do the test. It tells you what tests to do, but you don't really have an idea of why you're using it. So it's another example, I think, of a general problem of transparency in research, and the fact that we are sometimes at the mercy of software programs. We don't have the code. We don't have the documentation. And if we did have the code and we did have the documentation, we probably wouldn't understand it. So in summary, you may recognize by now that I don't have all the answers. In fact, you may be thinking, he doesn't have any of the answers. But I would conclude with some of these general statements regarding the contrasts that we see in all forms of biological research. Most research findings are false, but some are true. The glass is more than half empty, but I look at it from more of a positive standpoint because those findings which are true tend to be durable. False research findings tend to disappear and die a silent death. So the progress of science marches on based on true observations. There's an imperative for getting the truth now, but you can also say the truth will ultimately come out in the wash. I think that it's important to try to develop ways to make research more reproducible, but it's not going to be something that is going to be achievable even most of the time. NIH says requirements for rigor should be established. The competing view is these rigor requirements are stifling, restrictive, and expensive. And I think the current way they're making us write research grants is an example of that, and overkill. Literature lasts a long time. Be careful of what you publish. If you're starting off in an academic career and you look back 30 years at your publication record, what will you think? But as Dr. Fauci, America's greatest immunologist says, perfect is the enemy of the good. You're never going to do a perfect research study. Sometimes you have to have confidence that you're probably right and then move on. Statistics are the measure of God's purpose. I don't think there's any question that many research problems that we face require statistics. On the other hand, there's no law that says you can't win the Nobel Prize without doing statistics. Study the mathematical foundations of statistical inference, or do what PRISM tells you to do. The path to enlightenment is through your local biostatistician. The conflict is statistics is rife with controversy. And if you delve into statistical journals, you see there's a lot of disagreement there. So your local biostatistician is not necessarily going to have the answer for you. That's not to say you shouldn't get biostatistics help. In medicine, the problem comes to you. I used to do a lot of ER work, moonlighting, and one day a lady brought her dog in, and we actually did a lot for that dog. In research, you go to the problem. It's two different ways of looking at things. In medicine, you may be interested in a clinical problem, but the research tools and methods may not be there for you to really attack it incisively. So you have to make a decision on whether you're going to go after a problem, maybe have research, develop those tools on your own, or have tools and find problems that you can use, kind of like having a hammer and going around looking for a nail to hit. So those are the kind of conflicting conflicts that I think that we see in medical research. So thank you for your attention, and I'm happy to answer any questions.